This is SpaceTime Series 20, Episode 38. Coming up on SpaceTime, millions of monsters hiding in plain sight, Earth's mantle far hotter than previously thought, and Australian astronomy joins the Very Large Telescope Consortium. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have found evidence of a black hole hiding in a gas cloud in the dark corner of the Milky Way. The study, reported in the astrophysical journal Letters, is thought to be just the tip of the iceberg, with millions of these monstrous gravity wells thought to be floating around, unseen throughout the galaxy. However, so far, only about 60 have been found. Stellar mass black holes are most commonly born out of the supernova deaths of the largest stars. When these behemoths run out of hydrogen in their cores at the end of their lives, they begin fusing progressively heavier and heavier elements until eventually they produce iron. Since even the most massive stars can't fuse iron, the balancing act between gravity trying to collapse the star inwards and the energy from nuclear fusion in the core pushing the star outwards ceases, and gravity wins, causing the star to collapse in on itself in what astronomers call a core collapse or Type II supernovae, an explosion powerful enough to outshine an entire galaxy. These core collapse supernovae usually leave behind a stellar corpse in the form of a super-dense, rapidly rotating neutron star, an object with the mass of the Sun but compacted down to an object just 20 kilometers in diameter. However, the most massive of all stars are so huge, they collapse beyond the neutron star stage, forming a black hole, an object so dense with gravity so strong, the escape velocity becomes greater than the speed of light, 300,000 kilometers per second. And so nothing, not even light, can escape a black hole. Black holes are usually detected through the radiation they emit when they're feeding. However, because they emit no radiation when quiescent, they become almost impossible to detect and can only be located through the effect they have on the space-time around them. If a black hole is a companion star, gas streaming into the black hole from its binary partner tends to pile up around it, forming an accretion disk. The material in this accretion disk is crushed, stretched and ripped apart at the subatomic level by the immense gravitational pull of the black hole, in the process emitting intense radiation before passing a point of no return called the event horizon. Once beyond the event horizon, matter will fall forever into the black hole's singularity, a place where science's understanding of the laws of physics falls apart. However, if the black hole is alone in space, no emissions would be observable coming from it. The black hole in this study was discovered through an analysis of the motion of gas in an extraordinarily fast-moving cosmic cloud. Astronomers use the ASTI telescope in Chile and the 45-metre Nobiama radio telescope to observe molecular gas clouds around a supernova remnant known as W44, located some 10,000 light-years away. The authors were trying to examine how much energy was being transferred from the supernova explosion to the surrounding molecular gas. Instead, their observation showed signs of what appears to be a hidden black hole at the edge of W44. During the survey, the team found a compact molecular cloud with enigmatic motion. This cloud, named the Bullet, has a speed of more than 100 kilometers per second, which exceeds the speed of sound in interstellar space by more than 2 orders of magnitude. The cloud, which is some 2 light-years wide, is moving backwards against the rotation of the Milky Way galaxy. The observation showed that the Bullet seems to be jumping out from the edge of the W44 supernova remnant with immense kinetic energy. While most of the Bullet is expanding at about 50 kilometers per second, the authors found the tip of the Bullet has a speed of some 120 kilometers per second. The study's lead author, Masae Yamada from Japan's Keio University, says its kinetic energy is a few tens of times larger than that injected by the W44 supernova, and it would seem impossible to generate such an energetic cloud under ordinary environments. The team have now developed 2 possible scenarios to try and explain the formation of the Bullet. In both cases, a dark compact gravity source, most likely a black hole, plays an important role. The first scenario is known as the explosion model. It involves the expanding gas shell of the supernova remnant passing near to a static black hole. As it does so, the black hole begins to pull gas towards it, generating an explosion, which then accelerates the gas towards us after the gas shell has passed the black hole. Astronomers estimate that the black hole responsible for such a scenario would need to be at least 3.5 times the mass of the Sun. The second scenario, known as the eruption model, involves a fast-moving black hole blasting through a dense gas cloud. This gas is then dragged along by the strong gravity of the black hole, in the process forming a gas stream. Now, in this case, researchers estimate the black hole would need to be at least 36 times the mass of the Sun. The problem is, with the present data set, it's difficult to distinguish as to which scenario is more likely. The authors hope to disentangle the two possible scenarios and find more solid evidence for the black hole and the bullet with higher resolution observations using a radio telescope interferometer, such as ALMA, the Atacama Large Millimetre Submillimetre Array Telescope in Chile. This is SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. A new study claims Earth's mantle may be at least 60 degrees Celsius hotter than previously thought. The findings reported in the journal Science claims that while a 60-degree increase may not sound like a lot, especially when compared to the molten mantle's average temperature of more than 1400 degrees Celsius, it is highly significant because a hotter mantle would be far more fluid, helping to explain the movement of the planet's rigid tectonic plates. The Earth's mantle is a thick silicate rocky layer averaging about 2,886 kilometres wide, and making up about 84% of the Earth's volume. It lies between the Earth's superheated liquid iron outer core and the planet's solid crust. While the mantle is predominantly solid, it behaves very much like a viscous fluid when looked at over geological timescales. It moves through the process of convection, rising towards the surface at mid-ocean ridges, where it gradually spreads apart as tectonic plates along the seafloor, eventually running into subduction zones where it moves back down into the bowels of the Earth. Taking a closer look at these ridges, as new superheated mantle material rises to fill the void left by moving material on the surface, pressure decreases, causing the rocks to melt before eventually cooling down and solidifying to form new crust on the ocean floor. The study's lead author, Emily Serafian from MIT and the Woods Hole Oceanographic Institute, says the temperature of the Earth's interior affects everything, from the movement of tectonic plates to the formation of the planet. Serafian and colleagues wanted to model this process, and so needed to know the temperature at which rising mantle rock starts to melt. But determining that temperature isn't easy. Since it's not possible to measure the mantle's temperature directly, geologists have to estimate it through laboratory experiments that simulate the high pressures and temperatures inside the Earth. And water is a critical component of this equation. The more water, or actually hydrogen in the rock, the lower the temperature at which it will melt. The peridotite rock which makes up the upper mantle is known to contain a small amount of water. But the authors didn't know specifically how the addition of this water changes the melting point, so there's still a lot of uncertainty. To figure out how the water content in the mantle rock affects its melting point, Serafian conducted a series of lab experiments using a piston cylinder apparatus, a machine that uses electrical current, heavy metal plates and stacks of pistons in order to magnify force to recreate the high temperatures and pressures found deep inside the Earth. Serafian created a synthetic mantle sample using a known standardized mineral composition and then dried it out in an oven to remove as much water as possible. Until now, in experiments like these, scientists studying the composition of rocks have had to assume that their starting material was completely dry. That's because the mineral grains they're working with are far too small to analyze for water. After running their experiments, they then correct their experimentally determined melting point to account for the amount of water known to be in the mantle rock. Serafian says the problem with this is the fact that the starting materials are powders, and powders absorb atmospheric water, so whether you add water or not, there's still going to be some water in your experiment. Instead, Serafian modified her starting sample by adding spheres of a mineral called olivine, which occurs naturally in the mantle. The spheres were still tiny, about 300 micrometers in diameter, about the size of fine grains of sand. But they were large enough to analyze their water content using secondary ion mass spectrometry. From there, she was able to calculate the water content of her entire starting sample. And to her surprise, she found it contained approximately the same amount of water as what's known to be in the mantle. Based on her results, Serafian concluded that the mantle melting had to be starting at a shallower depth under the seafloor than previously expected. To verify her results, Serafian turned to magnetotellurics, a technique that analyses the electrical conductivity of crust and mantle under the seafloor. You see, molten rocks conduct electricity much better than solid rocks, and by using magnetotelluric data, geophysicists can produce an image showing where melting is occurring in the mantle. However, a magnetotelluric analysis published in Nature in 2013 by researchers from the Scripps Institute showed that mantle rock was melting at a deeper depth under the seafloor than what Serafian's experiment data had suggested. At first, Serafian's experimental results and the magnetotelluric observations seemed to conflict. Thing is, she knew both had to be correct. Reconciling the temperatures and pressures Serafian measured in her experiments with the melting temperatures from the Scripps study led to the startling conclusion that the oceanic upper mantle must be some 60 degrees Celsius hotter than current estimates. You're listening to Space Time. I'm Stuart Gary. And now we take a break from the show to talk about our new sponsor, Marley Spoon. One of the guys who helps me put SpaceTime together, Hugh, has been testing out Marley Spoon, and he wants me to try it as well because I'm a takeout sort of person. I don't cook. I can burn water. But Hugh's assured me that that's not a problem. Marley Spoon make it easy.
I'll tell you how easy they'll make it for you, Stuart. You're probably like most of us, and you probably hate going to the supermarket, going shopping, getting lost, and you wind up buying things you don't need. I got to tell you, Marley Spoon supply you with exactly what you need, and that's it. You're not tempted into buying lots of extra rubbish and stuff like that. And all your meals arrive pre-portioned, so they're ready to go. They're in separate bags, and you just pop them in the fridge and grab them out when you're ready to cook. How simple is that? You come home from work, you're tired, whatever, go to the fridge, say, oh yeah, tonight I'll have the chicken cacciatore. You pull the bag out, there's all the ingredients, there's the recipe card, you make it, you eat it. Simple.
Because the big problem about eating takeout is it's not cheap, it's expensive. I mean, you buy a meal for yourself and a few other people and you're up for $50 easy.
Yep. And that's another reason why you should try Marley Spoon, Stuart, because it's not expensive. In fact, you're going to save money because you're going to save money at the supermarket. But when you sign up, we will even save you even more money because as a fan of SpaceTime, you can get $35 off. Just go to marleyspoon.com.au if you're listening to us in Australia and use the code SPACE at checkout. We'll get you $35 off your first order. And if you live in North America, in the USA, go to marleyspoon.com and use the code SPACE and you'll get $30 off your first order.
So Marley Spoon, changing the way you cook. And now, back to our show. The Australian federal budget handed down last week in Canberra included some good news for astronomers with the announcement of a new strategic partnership providing access to one of the world's best astronomical facilities, the European Southern Observatory's VLT, or Very Large Telescope. The 10-year, $26.1 million deal provides Australian researchers with telescope time on the four 8.2-metre telescopes at the Chilean Observatory. It also provides the European Southern Observatory with greater access to cutting-edge Australian astronomical technology, now being developed for the next generation of super telescopes such as the Giant Magellan. The new arrangements, which begin next year, also includes ongoing funding of around $12 million a year until 2027-28. The deal is part of a major revamp of Australian astronomy by the federal government, with a new coalition of Australian universities being set up to operate the Australian Astronomical Observatory's Anglo-Australian Telescope at Siding Spring. The changes will see most, if not all, of the Australian Astronomical Observatory's operations taken over by other bodies. The Australian National University, Astronomy Australia Limited, and other national research institutions have for several years identified a critical need for Australian astronomers to have access to large optical telescopes through an international partnership. Professor Matthew Collis from the Australian National University describes the new agreement with the European Southern Observatory as a far-sighted initiative.
This is a huge change for Australia. We've been trying to join the European Southern Observatory now for 2 decades. I remember an initial attempt to do this in the mid-1990s, and it's been sitting at the top of our wish list for the last 2 decadal plans. So we're delighted that this strategic partnership is the first step in fully joining the European Southern Observatory.
What will that mean for Australian astronomy?
Well, the strategic partnership means that for the next 10 years, we will have access to the 8-metre class telescopes that the European Southern Observatory runs at its Lucia Paranal Observatory, as well as a range of smaller telescopes they also have there. In effect, this means that we get about a 30% share in an effective 8-metre class telescope, and that's about 50% more time in one of those premium optical telescopes, the best in the world, than we've ever had before.
Tell me about the VLTs.
The VLTs are 4 8-metre telescopes on a very good site at Paranal in the northern Andes in the Atacama Desert. They've got a lovely clear site with very good seeing, so they're great for astronomical observation. They're 4 extremely well instrumented telescopes, and because there's 4 of them, there's a wide range of instruments on them, so there's something there for everyone to use, and they're very well run by the European Southern Observatory. In fact, many people would argue they're the best set of telescopes on the planet.
Now, as well as having 4 telescopes which can each operate independently, they can also be joined together and operate as an interferometer, can't they?
They can, that's right. In fact, as well as the 4 big telescopes, they also have some smaller 1.8 metre, what they call outrigger telescopes, which can be moved around into different configurations, and that allows all these telescopes to operate as one and to take much sharper images than any single telescope could do. And in fact, they've just started commissioning a brand new instrument called Gravity, which is intended to take full advantage of the VLT interferometer capabilities.
ESO gets something out of this too, don't they? They get access to Australian technology.
They do indeed. I mean, let's not forget, we're paying about $12 million a year for 10 years, so they're getting $120 million out of this, and they're using that to upgrade all their facilities. So they're getting a big boost in the amount of funding they have, but they are also getting access to our extremely strong astronomical instrumentation programs and our technology. We are, without question, a leading force in that field, and we build some of the best instruments on the planet. We're building 2 of the 4 instruments for the Giant Magellan Telescope. We've previously built the OzPOS fiber positioner for the VLT, and we're currently building the ESOP fiber positioner system for the Vista 4-metre telescope that ESO owns. So we've built instruments for ESO before. They appreciate what we can do, and now we're part of their team, as it were. We hope to do a lot more.
In 10 years' time, what happens when the current deal runs out? Are you going to look for an expansion, or is it too early to say? By that I mean going to other telescopes they operate, like ALMA and the new super telescope they're building.
The Australian community would certainly very much like to join ESO as a full member, giving us access to ALMA as the world's best submillimetre and millimetre array radio telescope, and of course the European Extremely Large Telescope, which when it's built will be the largest in the world. If we did that, then we'd have access both to the Giant Magellan Telescope, which will have the widest field of all the next generation optical telescopes, and to the European Extremely Large Telescope, which will have the best resolution and the biggest collecting area. And so that would put us in an incredibly strong position for the future. But that's 10 years off, and we've got to work towards that. And if we're going to make a success of this, then we need to make sure that ESO appreciates our membership. So we need to make ourselves indispensable by doing a good job building instruments for them and being good community members. In astronomy, we punch way above our weight because we have invested in it, and we've got a stunningly good tradition, and we've managed to keep on supporting the technology. And this is why that we're welcome partners and indeed leaders in things like the Giant Magellan Telescope, the Square Kilometre Array, and why we expect that we will punch well above our weight within the European Southern Observatory as well.
That's Professor Matthew Collis from the Australian National University. The 2017 federal budget also saw a further drop in real funding for several of the nation's leading scientific research organisations, including the Australian Nuclear Science and Technology Organisation, ANSTO, and the Commonwealth Scientific and Research Organisation, the CSIRO. The CSIRO had already been hard hit with massive budget cuts under the Abbott government, resulting in significant job losses and many Australian scientists heading overseas to greener pastures. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.
This edition of SpaceTime is brought to you by Marley Spoon. Marley Spoon's mission is to make incredible home cooking available to everyone by turning you into an instant gourmet. Choose your own menu with lots of new recipes every week. And as a special incentive for Australian listeners, if you go to marleyspoon.com.au, you'll get 35 Aussie dollars off your first order when you use the special code SPACE at the checkout. And for American listeners, go to marleyspoon.com and get $30 off your first order when you use the code SPACE at the checkout. Marley Spoon, changing the way you cook.